A group of physicists once stared at an atom so hard it forgot how to die. No, that's not a metaphor for grad students stuck in the lab at 3 a.m. That's the Quantum Zeno Effect. Imagine reality itself freezing simply because you looked at it, like giving the universe stage fright. A particle poised to change, decay, or do something interesting suddenly halts mid-act because you wouldn't stop peeking. Welcome to physics, where curiosity literally kills the motion. This isn't TT philosophy class, where you sip coffee and wonder if the chair exists when you were not looking at it. This is physics, lab coats, lasers, data, hard science that says, surprise, your gaze has superpowers. Every time you observe a quantum system, you're not just watching, you're meddling. It's like trying to watch a toddler eat without them noticing. The second they see you, they freeze, fork in midair, crumbs on their face, waiting to see what you'll do. Observation isn't passive. It's the nosiest, most intrusive act in the universe. The effect takes its name from Zeno of Elea, an ancient Greek philosopher who believed motion itself was an illusion. He'd probably laugh himself into a toga knot if he knew that 2,000 years later, physicists proved him kind of right. At the quantum level, things really do hesitate to move when you won't stop checking on them. Imagine trying to leave a party, but everyone keeps shouting, "Wait, where are you going?" Suddenly, you're stuck explaining yourself for hours. That's the atom's life now. Endless interruptions. The actual science runs like this. Normally, an unstable quantum system, say an excited atom, would naturally evolve, decay, and settle down. But if you keep measuring it every nanosecond, you keep forcing it back into the about-to-change position. Reset, reset, reset. Like hitting pause on Netflix every time a character blinks. After a while, nothing moves, nothing evolves, and you're left wondering if the remote is broken. And the kicker? This isn't a thought experiment anymore. We've done it. We've gone full cosmic helicopter parent. Scientists built setups with lasers and traps and stared at atoms so relentlessly, the atoms just gave up trying to decay. You can practically hear the particles groaning. Fine, I'll just sit here. But stop looking at me, you creep. It's not metaphysics. It's measurable, testable. And it throws a big middle finger at our classical assumption that the universe just goes on, whether or not we re-paying attention. And before you ask, no, it doesn't mean your crush will stay in the room if you stare at them long enough. Reality only breaks down at the quantum level. At the human scale, if you stare too long, you just get pepper sprayed. But the principle remains jaw-dropping. The act of observation literally prevents change. Physics has become the ultimate nosy neighbor, leaning out the window, making sure nothing on the street happens unless they approve. Think about it. The universe is supposed to be this great unstoppable machine. Stars burn, atoms decay, time marches on. But quantum mechanics laughs in our face and says, only if you look away. The cosmos, it turns out, is a terrible performer. It won't finish the song if it sees you recording. It freezes, stuck in the same verse, waiting for you to blink. And the moment you do, boom! The show goes on as if nothing happened. That's why the Quantum Zeno Effect has been called one of the weirdest proofs of quantum measurement. Not because it's confusing, though it is, but because it makes reality feel like it's auditioning for a bad improv class. You clap, it pauses. You stop clapping, it continues. Reality is basically playing red light, green light with us. And somehow, we keep winning. And maybe you're already thinking, wait, if watching stops reality, Does that mean the entire universe is one giant surveillance problem? Who's observing us? Yeah, don't go down that rabbit hole just yet. Save the existential crisis for later. For now, just marvel at the fact that atoms can be bullied into immobility by a pair of human eyes, or even by a cold, unblinking detector with no feelings whatsoever. Turns out, the machines don't just record reality, they edit it. So buckle up, because we're not just dabbling in philosophy. This is physics with receipts, atoms that freeze on command, systems that obey the tyranny of the observer, and a universe that might only be moving when you're not paying attention. By the way, if this kind of quantum nonsense excites you, smash that like button, subscribe, and tell me in the comments where you're watching from. Because while the universe may hesitate under observation, the algorithm doesn't. It only moves when you poke it. And the real fun? Well, that begins the moment we ask how ancient Greek paradoxes, skeptical physicists, and a couple of overeager laser beams turned into proof that watching is the same as interfering. Picture a bearded Greek man in sandals, squinting at the world like it's a badly written math problem. That was Zeno of Elea. Around 2,500 years ago, Zeno argued that motion was impossible. His logic? If you want to walk across a room, first you must go halfway, then halfway again, then halfway again. Infinite halves later, you're still stuck in place like a medieval PowerPoint slide. People laughed, shrugged, and kept walking. But Zeno smirked, probably whispering, "Checkmate, joggers." What nobody expected was that physics would one day nod politely and say, well, he wasn't completely wrong. Fast forward to the 20th century, and the quantum world popped up with its own version of Zeno's headache. Instead of people trying to cross a room, it was particles trying to evolve in time. Instead of endless halfway points, it was endless measurements. And instead of ancient philosophy class, it was 1977, in a paper written by two physicists, Misra and Sudarshan. Their claim? If you measure a quantum system constantly, it never gets the chance to change. Congratulations! You've just invented the cosmic equivalent of staring at bread in the oven so obsessively that it refuses to rise. Now, in normal life, observation doesn't stop things from happening. Your pizza won't freeze because you're glaring at it. The milk doesn't stop spoiling when you check the expiration date every 5 minutes. But the quantum world is petty. The act of checking interrupts the system, collapses its wave function, and slaps it back into the same state over and over again. Misra and Sudarshan did the math and realized observation wasn't passive. It was sabotage. When their paper came out, most people thought it was a curiosity, maybe a weird logical trick, something best discussed after a few drinks. After all, physics was already drowning in paradoxes. Schrödinger had his undead cat. Heisenberg had uncertainty. Einstein had spooky action at a distance. Adding particles too shy to evolve if you look at them sounded like another item on the physics comedy menu. But buried under the math was a brutal message. The universe doesn't evolve independently. It evolves conditionally, depending on whether or not you're nosy enough to keep checking. And of course, naming it after Zeno was too delicious to pass up. The man who said motion was an illusion accidentally became the mascot of quantum mechanics' most awkward quirk. Somewhere in the afterlife, Zeno probably dropped his wine goblet in shock when he learned that, yes, motion really does break down if you look too often. His entire philosophy went from annoying Greek thought experiment to peer-reviewed journal citation. That's one way to win an argument 2,000 years late. But the Misra-Sudarshan paper wasn't all dusty logic. It had teeth. It implied you could actually manipulate quantum decay by timing your observations. Think about that. For all of human history, decay was the one constant. Fruit rots, stars burn out, your phone battery dies 5 minutes into a road trip. Yet suddenly, two guys with chalkboards were saying, "Wait, if we just keep watching, decay hesitates." That's not just theory, that's weaponized curiosity. Naturally, physicists were skeptical. The idea sounded like cheating. In the lab, observation had always meant measurement, and measurement had always meant destruction. Try measuring an electron's position, you ruin its momentum. Measure its momentum, kiss its position goodbye. Measurement was the cosmic wrecking ball. Now, Misra and Sudarshan were saying the wrecking ball could also act like duct tape, holding the system in place. It was like finding out your clumsy roommate, who usually breaks everything, has a hidden talent for origami. And yet, the math refused to budge. Quantum mechanics already predicted bizarre things, but this one carried the insult of simplicity. It didn't require exotic fields, mysterious forces, or alien particles. It only required persistence, the kind of annoying persistence usually reserved for telemarketers and toddlers. Just keep asking. Are we there yet? At such a rapid rate that the trip never even begins. The paper sparked debates. Was this a genuine feature of quantum mechanics, or just an artifact of the equations? Could observation really stretch out unstable states? The physics community wrestled with it, oscillating between laughter and unease. Because if it was true, it meant control. And control at the quantum level was the holy grail, a way to tame particles that normally behave like drunk cats in a laser pointer factory. And let us be honest, physicists love nothing more than proving philosophy students right for all the wrong reasons. Zeno said you'd never get across the room? Fine. Maybe not if you're an atom. Misra and Sudarshan's paper elevated a dusty paradox into a scientific principle, making "motion is an illusion" sound less like a wine-soaked debate and more like a potential research grant. But there was a problem. Back in 1977, the math was elegant, but the experiments to prove it weren't yet possible. Technology lagged behind the theory, so the Quantum Zeno Effect sat in limbo. A paradox in waiting, an idea too bold to dismiss and too slippery to confirm. It lingered like a rumor at a high school dance. Everyone heard about it. Nobody was sure if it actually happened, and half the people assumed it was exaggerated. Still, the seed was planted. Observation might freeze reality. All that remained was for some overworked experimental physicists with enough lasers, magnets, and spare funding to test it. And if there's one thing physics never resists, it's an opportunity to catch reality breaking its own rules under surveillance. Physicists discovered long ago that quantum particles are indecisive wrecks. Electrons don't politely choose a seat. They smear themselves across every row like teenagers at a movie theater. A single photon doesn't march down one hallway. It slithers through all the hallways at once, like a bored cat pushing open every door in your house. This is what they call a superposition, the ability to exist in many states simultaneously. Because commitment is for classical objects like rocks and tax accountants. Then along comes measurement, and suddenly, the party ends. The second you check what state the particle is in, it collapses into a single option, as if the universe just yelled, "Pick a side already." That collapse isn't metaphorical. It's an actual physical event where the cloud of probabilities gets strangled into a definite outcome. Before the measurement, an electron can be everywhere. After the measurement, it's here. Your act of peaking is like throwing a bucket of cold water on the system's quantum indecision. The strange part is that this collapse happens every single time you measure, and the Quantum Zeno Effect weaponizes that fact by doing it over and over again. Imagine someone forcing you to answer the same yes or no question 10,000 times in 1 second. You'd lock up too. That's what happens to quantum systems. Their natural tendency to evolve in time gets continually interrupted by a barrage of observations. Each observation resets the wave function, slamming the brakes before the system can make progress. Think of it as trying to watch a progress bar load on your computer. Every time you refresh the page, the bar jumps back to 0 and starts again. The program never finishes because you can't keep your hands off the mouse. The system isn't broken. You're the problem. Observation is like a cosmic refresh button, resetting the quantum browser before it loads the next page of reality. And if you want to get more unsettling, this isn't just a thought game. It means observation isn't some neutral bystander. It isn't the lab coat in the corner taking notes. Measurement is a direct participant, a clumsy guest at the party who keeps knocking over drinks. When you look at a quantum system, you don't just learn about it, you force it to choose a specific reality. The universe isn't handing you a receipt for what it already did. It's more like a waiter nervously scribbling your order the moment you start watching, and suddenly the menu changes under your nose. This is why physicists argue endlessly about what measurement really is. Some say the wave function is real, and observation actually crushes a multiverse of possibilities into one chosen branch. Others claim the wave function was only a tool for predicting probabilities, and collapse is just bookkeeping. Either way, the undeniable fact is that observation leaves fingerprints on the outcome. You're not Sherlock Holmes deducing what already happened. You're more like the suspect's mother showing up in the interrogation room, changing the story by sheer presence. The weirdest part? Even when no human eyes are involved, the effect holds. Machines, detectors, sensors, they all count as observers. A camera left running in the lab influences the result, even if no graduate student ever watches the tape. The measurement doesn't care whether a conscious brain processes it. The act of registering information at all is enough. So no, your thoughts alone can't freeze reality, but your particle detector can. Humanity doesn't get Jedi powers, but our gadgets apparently do. If this still feels slippery, let's stretch the analogy. Imagine you're on stage, about to perform. If no one's in the audience, you feel free to improvise wildly, juggling flaming knives, breakdancing, singing off-key. But the second a crowd appears, you stiffen up. You pick one act, you stick to it, you stop experimenting. Observation has caged you into a single performance. Quantum systems behave the same way. They experiment in private, but under surveillance, they conform. Reality itself is apparently camera-shy, and that's why constant observation freezes them. Every fresh act of measurement cuts off all possible evolutions except the one they're already in. Over time, this produces the illusion that nothing changes. But it's not an illusion. It's physics doing the equivalent of shoving the same VHS tape back into the player every half second. Watch closely enough, and the movie never advances beyond the first scene. Now, the mathematics behind this is brutal but straightforward. The probability of a system changing is proportional to time. Slice time into absurdly small intervals, and that probability approaches 0. Keep measuring during those intervals, and the wave function collapses right back into its starting point each time. It's like trying to take a step forward, but a referee blows the whistle after every millimeter and forces you back to the line. Quantum evolution keeps getting interrupted by referees with whistles made of lasers. And this doesn't just apply to single particles. Entire atomic systems can be locked in place if they're continuously monitored. Gas clouds, trapped ions, even radioactive samples have all been subjected to this quantum freeze frame. Each time, the result is the same. The more you watch, the less they move. Reality gets stage fright across the board, from lone electrons to entire clusters of atoms. It's a universal problem, not a quirky footnote. Which brings us to the unsettling part. If observation can halt quantum evolution, then time itself might not be as smooth as we like to pretend. Because if you can interrupt a system's forward march just by staring at it, what does that say about the underlying machinery of reality? Physicists are nothing if not stubborn, and the idea that you could paralyze a quantum system by staring at it was too tempting not to test. So they built elaborate traps for atoms, devices with lasers arranged like prison bars, magnetic fields curled tighter than a miser's fist, and vacuum chambers polished until the janitors begged for mercy. Inside these cages, atoms floated weightless, as defenseless as bugs under glass. Then came the experimenters, squinting at them through detectors, ready to find out if attention really does pin reality to the wall. And the results? The atoms sulked. Normally, they would decay, emit light, or shuffle into lower energy states. But under constant observation, they lingered in their original condition, as if pretending nothing was wrong. The more insistently the physicists measured them, the longer the atoms stayed frozen. It was like watching a child caught with stolen cookies, eyes wide, unmoving, refusing to chew until the adults looked away. This wasn't superstition. It was clockwork, measurable and infuriating. Unobserved, the system marched along its expected timeline. Decay rates matched predictions, lifetimes ticked on schedule. But add continuous measurement, and everything slowed down, like a cosmic bureaucrat stamping pending on every application. For once, the universe wasn't running late because of complicated math. It was late because we wouldn't stop nagging. One of the first successful demonstrations came in the 1990s, when experimentalists trapped beryllium ions and monitored them with pulses of laser light. Left alone, the ions decayed just fine. With rapid-fire observation, they stubbornly refused. It was physics' version of "a watched pot never boils." Except this time, the pot really didn't boil. The data proved that attention wasn't metaphorical. It had teeth. Later experiments pushed further. Clouds of cold atoms were locked into place using an optical lattice, essentially a laser-made egg carton that forced particles into neat little wells. Repeated measurements kept them from tunneling out of their traps. Without the monitoring, the atoms would have hopped around freely like drunk grasshoppers. With it, they stayed glued to their slots, as if the entire quantum world had been enrolled in mandatory detention. These setups weren't just technical marvels. They were precision nightmares. The margin for error was so tiny that one stray vibration, one cough from a grad student could scramble the data. Yet time after time, the results came out the same. Observation stretches the lifetime of unstable states. Quantum systems don't evolve smoothly. They evolve under duress, waiting for us to blink. Imagine how infuriating this was for the researchers. You spend decades building theories about natural decay rates, energy transitions, and tunneling probabilities. Then you turn on a detector, and all your precious predictions melt into nonsense because the system refuses to budge. It's like training a dog to fetch, only to discover that the dog will fetch precisely nothing if you keep staring at it too closely. Even radioactive decay, the poster child for unstoppable processes, wasn't immune. Experiments showed that by carefully timing observations, decay probabilities could be nudged away from their expected paths. This didn't make atoms immortal, but it stretched their lifetimes in measurable ways. Radioactivity, the phenomenon that powers nuclear reactors and terrifies airport security, suddenly looked less inevitable. Apparently, even uranium gets bashful when too many eyes are on it. And then there were photons. Light, the most basic messenger of the universe, could also be bullied into submission. Physicists designed setups where single photons tried to pass through interferometers, devices meant to split and recombine beams. Continuous observation at key points forced the photons into predictable, repetitive behaviors, blocking the chaotic spread they would normally exhibit. Watching light changed light. The very act of checking where a photon was going turned it into a cosmic deer frozen in headlights. None of this should have been possible if physics were a neat, mechanical machine. Atoms don't know they're being watched in any human sense, yet the equations governing them shift under scrutiny. It's not psychology, it's probability functions being strangled by interference. But the outcome looks suspiciously like paranoia. Left alone, atoms behave freely. Under surveillance, they lock up. Reality doesn't act like a clock, it acts like a nervous witness under cross-examination. And the creepiness only deepens when you realize this happens across scales. It's not just lonely particles in esoteric experiments. The principle extends wherever quantum rules dominate. Semiconductors, superconductors, even biological systems on the edge of quantum coherence. The lab results weren't curiosities. They were blueprints, showing us that reality can be bent, delayed, and manipulated simply by refusing to look away. Which, of course, begged the next dangerous question. If observation freezes systems, how small must the window be to catch them? Because quantum evolution doesn't unfold like a continuous movie reel. It ticks in probabilities, jagged jumps, fleeting intervals so short they make nanoseconds look like geological ages. The timing of our stare might be the key to locking reality in place, or letting it slip through our grasp. If you want to understand why the Quantum Zeno Effect works, you have to wrestle with the most slippery thing in physics: time. Not the neat ticking on your wall clock, but the jittery microstructure that only shows up when you zoom so far in that seconds look like geological epochs. Down there, time isn't smooth. It's lumpy, jittery, and probabilistic. It's the kind of clock that looks broken but still charges you rent. Here's the trick. Quantum systems don't slide from one state to another like a ball rolling downhill. They creep, hesitating in short bursts, with the likelihood of change growing as the intervals stretch out. At absurdly small timescales, the probability of transition is practically zero. You can almost hear the particle mutter, "Not yet. Give me a second." Except its second is a trillionth of your seconds. Catch it during that window, and it hasn't had time to evolve. Interfere again right away, and you yank it back to the starting line. Do this rapidly enough, and the system never gains momentum to change. It's like interrupting someone's sneeze over and over. Eventually, they just sit there red-faced, stuck mid-gesture, eyes watering, waiting for mercy. Time gives the sneeze its opening. Observation slams the door shut. The mathematics is merciless. At extremely short intervals, the survival probability doesn't decrease linearly with time. It decreases quadratically. That means the system is extra sticky near the beginning, reluctant to budge. Keep cutting time into those tiny chunks and slamming the system with measurement, and the chance of motion drops even further. It's not sorcery. It's math gleefully laughing at your classical intuitions. Imagine trying to run a marathon, but every millisecond someone shoves you back to the starting line before you can lift your foot. You're not slow, you're sabotaged. That's how quantum systems feel under rapid observation. The race of natural evolution never begins because the referee is obsessed with restarts. Time is still ticking, but progress is denied. This timing sensitivity is why the Zeno effect doesn't show up on everyday scales. By the time you check if your toast is burning, the probability has had plenty of opportunity to evolve into, yes, it's already smoke. At atomic timescales, though, the delay before significant change is long enough for us to poke, prod, and slam the reset button repeatedly. Ordinary people can't freeze reality, but experimentalists armed with femtosecond lasers absolutely can. Physicists exploited this by building measurement routines faster than the system's natural evolution. The shorter the interval, the stronger the freeze. Push it to extremes, and atoms linger in states far past their expiration dates. It's like keeping milk fresh by inspecting it every nanosecond. As long as you don't stop checking, the smell never changes. The absurdity is that this actually works, not in your fridge, but in the vacuum chamber of a quantum lab. And if this makes your head spin, that's because you're wired to think of time as a river flowing evenly forward. Quantum mechanics insists it's more like a strobe light, flickering possibilities on and off so fast you mistake it for continuity. Observation matches that flicker, snapping the system back before the next flash can reveal motion. In other words, reality is less of a movie reel and more of a slideshow that panics whenever you hold down the projector button. It also means that measuring too slowly ruins the trick. Give the system enough breathing room, and it starts evolving again, leaping past the sticky region of short intervals. The freeze only works if you hammer time with interruptions so relentless that no progress sneaks through. Measurement becomes less like curiosity and more like harassment, pinning reality into submission with stopwatch precision. Even worse for your sanity, the boundary between too fast and too slow is razor thin. Miss the window, and the system slips free. Hit it exactly, and you've built the cosmic equivalent of a pause button. Its timing is torture. Press often enough, and the prisoner never leaves the cell. Wait too long, and they're gone. Reality, it turns out, isn't just camera-shy, it's chronophobic. This dependence on time sparked a wave of new experiments. Scientists developed ultra-fast measurement tools to catch transitions at the exact moment when probability curves were most fragile. Femtosecond spectroscopy, pulsed lasers, superconducting detectors, all engineered to exploit that fleeting interval when nature hesitates. The lab became less about observing systems and more about ambushing them in their most vulnerable microseconds. And it worked. Atoms that should have flipped, photons that should have tunneled, nuclei that should have decayed, all stalled under the tyranny of precise timing. Not because we added energy, not because we rigged the conditions, but because we insisted on staring so quickly and so often that the system ran out of chances to move. The stopwatch became the weapon, which left physicists staring at a darker implication. If observation could freeze quantum systems by exploiting time's fragile intervals, then perhaps observation could also bend those intervals in the other direction. If you could mistime your interference, maybe you could accelerate change instead of halting it. Suddenly, the question wasn't just about keeping reality still. It was about controlling its tempo.
For years, physicists thought observation only paralyzed systems. Keep checking and nothing happens. Great, mystery solved, let's go home. But then came the plot twist. Under the right conditions, watching doesn't freeze particles at all. It makes them move faster. Suddenly, the same scientific nosiness that once pinned atoms in place started shoving them forward like a pushy parent at a talent show. This reversal became known as the Anti-Zeno Effect, because science can't resist naming things like sequels. Same cast, different ending. Instead of time stretching into paralysis, measurement injected extra chances for change. It was as if reality got tired of your interruptions and decided, fine, let's get this over with, before sprinting ahead. The mechanism is sneaky. If your observations aren't rapid enough to trap the system in its sticky short-time window, each measurement still disturbs the wave function. But now that disturbance pushes the system toward new states instead of yanking it back. In practice, this accelerates decay. Instead of freezing an unstable nucleus, you prod it into falling apart faster. Imagine taking a fragile vase and checking on it every few seconds by tapping it with a hammer. Don't be surprised when it shatters quicker than expected. The first experiments confirming this weren't done in some abstract chalkboard fantasy. They involved real atoms and real detectors. Researchers timed their observations just outside the protective window where freezing worked, and the systems obligingly crumbled. Ions decayed faster, photons escaped sooner, and unstable states rushed headlong into collapse. The lesson? Attention isn't neutral. It's either a straitjacket or a turbocharger, depending on how you wield it. This made physicists profoundly uncomfortable because the very thing they thought was passive, measurement, turned out to be the steering wheel. You weren't just recording reality. You were scheduling its pace. The universe didn't hand you answers. It waited for your stopwatch to dictate whether things slowed down or sped up. It was less like science and more like stage management, with reality as the reluctant actor who resents both under-rehearsal and over-rehearsal. The Anti-Zeno Effect wasn't a quirky exception. It was mathematically inevitable. If you vary the timing of interventions, the system's probability curve can be bent in either direction. The observer isn't just a referee, they're an accomplice, fiddling with the tempo of the match. One miscalculated interval, and instead of freezing the player, you've sent them sprinting for the goal. This discovery opened unsettling possibilities. Nuclear decay, once thought untouchable, could in principle be sped up with the right measurement schedule. The same process that powers reactors and bombs might be coaxed to hurry along by nothing more than persistent meddling. Engineers began asking if controlled observation could tweak material lifetimes, influence qubits, or modulate chemical reactions. Suddenly, peaking wasn't just sabotage, it was a tool. The duality of freeze versus acceleration turned the entire conversation upside down. The Zeno effect alone could be dismissed as a weird party trick of physics. But paired with its evil twin, it revealed something deeper. Time evolution is negotiable. Nature doesn't just roll forward on autopilot. It waits to see how often you're going to interfere. It's as if reality has a customer service line, and each call you make either holds the system on pause or shoves it into fast forward. The philosophical implications were unbearable for some. If observation alters not just what happens, but when it happens, then time itself is entangled with the act of watching. You can no longer separate the arrow of time from the meddling of measurements. The clean divide between passive observer and independent system disintegrated. Scientists used to complain that observation destroyed quantum states. Now they had to admit it also played conductor, waving the baton to set the tempo of decay. The sheer absurdity begged for comparison. It's like opening your fridge to check if the milk has spoiled, and depending on your timing, either stopping the rot completely or making it sour faster. Reality becomes the worst roommate imaginable. One day it won't move unless you nag it constantly, the next it deteriorates faster just to spite you for looking. Either way, you're left questioning whether you should have peaked at all. Experiments multiplied. Cold atoms in optical lattices, superconducting qubits, trapped ions. All of them showed the same dual behavior. Measure aggressively and systems linger. Measure at intervals just long enough, and they collapse quicker than their natural lifetimes. This wasn't limited to one lab or one type of setup. It spread across the quantum zoo, making it clear that the phenomenon wasn't a quirk. It was a law. Observation was no longer the passive notebook in the corner. It was the metronome setting the beat of reality's symphony. And of course, once you can manipulate the tempo of quantum systems, the next question practically screams itself. Could this extend to more complex structures? Could whole assemblies of particles, molecules, or even biological systems have their lifespans adjusted by sheer interference timing? Because if the answer is yes, then the act of watching doesn't just alter reality. It rewires the very rhythm of existence. Physics labs weren't the only places haunted by the Zeno problem. Soon, biologists started to wonder whether the same tricks of time and observation might lurk in living systems. Because if atoms and photons could be bullied into stillness or acceleration, why not proteins, cells, or even nerves? Cue the uncomfortable realization that your own body might be running on rules better suited for a particle circus than a physiology textbook. Take photosynthesis. Plants aren't just green decorations, they're quantum hustlers. Inside their chlorophyll, energy travels through molecules with efficiency that engineers would sell their kidneys for. The process looks suspiciously like quantum coherence, waves of energy exploring multiple routes at once before choosing the fastest. The catch: that coherence is fragile. Disturb it too much and the whole miracle crashes. Observation, even indirect, could alter how the energy hops. Nature itself may be fine-tuned to walk a line between freezing and acceleration. Sunlight fuels life, but the hidden gears run on physics that gets stage fright. Then there's the brain. Neurons don't fire on quantum logic in the casual sense. You won't catch your thoughts existing in superposition like Schrödinger's shopping list. But at microscopic scales, ion channels and neurotransmitter releases dance close enough to quantum effects that some researchers wonder if timing can alter their behavior. The Zeno principle suggests that if certain biochemical states were measured often enough by proteins, enzymes, or molecular detectors, they might linger longer than expected. In other words, biology may already be exploiting quantum foot-dragging for survival. That idea sounds wild, but biology is nothing if not opportunistic. Evolution has a track record of stealing every possible advantage. Birds navigate with magnetic fields that involve quantum entanglement. Smells may be detected using molecular vibrations that echo quantum tunneling. If plants and animals are already dabbling in these tricks, the possibility that observation-like mechanisms affect lifespan or reaction speed isn't just sci-fi rambling. It's plausible. Nature has no shame about hijacking physics for profit, and the implications only get weirder. If quantum Zeno-like behavior influences biological systems, then watching might not mean human eyes or lab detectors. It could mean internal monitoring, molecular checkpoints inside cells that constantly check in on states. This constant surveillance could keep unstable processes from decaying too quickly or, in reverse, could accelerate transitions when timed poorly. Your own body might be filled with microscopic supervisors, ensuring that certain reactions freeze long enough to complete, while others rush ahead before chaos sets in. It's less like a machine and more like a nervous bureaucracy. Consider DNA. It's not just a passive library. It's under constant scrutiny by repair enzymes patrolling for damage. When they inspect too frequently, certain mutations may be stalled, trapped before they spread. Check too slowly, and errors propagate. The same dynamic reeks of the Zeno game. Surveillance locking states or rushing them depending on the timing. Your genetic material may owe its stability not just to chemistry, but to physics' obsession with being noticed. And what about consciousness itself? Some theorists, reckless enough to gamble reputations, have proposed that awareness could hinge on quantum coherence in neural microstructures. If so, the act of monitoring states inside the brain might stretch or shrink their lifetimes. In that model, the very flow of thought could be governed by whether quantum processes are frozen into coherence or collapsed into noise. It's speculative, but the mere possibility that your inner monologue depends on physics getting performance anxiety is both hilarious and terrifying. Medical science hasn't ignored this circus. If observation alters decay rates, then targeted measurement could one day influence cell death, protein folding, or even disease progression. Imagine a treatment where carefully timed scans don't just reveal a tumor, but slow its growth by repeatedly catching unstable molecular processes. Or imagine misapplied observation accelerating deterioration, like a doctor accidentally fast-forwarding your cells into chaos. Medicine already struggles with side effects. Adding quantum Zeno manipulation would turn hospitals into probability casinos. And yes, this creeps into technology that interfaces with biology. Quantum sensors designed to detect faint signals may inadvertently alter the very systems they're measuring. Scan a neuron too aggressively, and you might not just observe its firing. You might be changing its firing pattern. The patient wouldn't just be under observation. The observation itself would be part of the treatment, whether anyone intended it or not. What started as an obscure mathematical prediction now touches the possibility of life itself, running on these fragile principles. The line between physics and biology blurs into a mess where atoms, proteins, and cells all play by the same paranoid rules. Watching changes the act, and timing dictates whether the show stalls or accelerates. That's not just a lab trick. It hints at a universe where survival may rely on mastering when to look and when to look away, which leaves the uncomfortable thought hanging. If biology already exploits these quirks, then perhaps our own perception, our conscious awareness, might not just witness the world, but sculpt its pace with every glance. Physicists couldn't just leave the Zeno effect in dusty journals. They smelled utility. If staring at particles could freeze or speed them, then detectors weren't just tools of measurement, they were control levers. Enter the age of engineering reality by weaponizing attention, with labs gleefully turning observation into a design feature instead of a nuisance. The first playground was quantum computing. Qubits are notoriously unstable, decaying into useless mush the moment you ask them a hard question. Normally, that's a disaster. But if constant interrogation keeps a state alive, then strategically timed measurements could act like a life support machine. Researchers realized they could prevent qubits from collapsing by rhythmically checking on them, turning the Zeno effect into a digital babysitter. In other words, Google's dream of a quantum processor might rely on physics behaving like an overprotective parent, refusing to let its child leave the house. Then came quantum error correction. Traditional computers rely on redundancy, triple backups, error codes, safety nets. Quantum versions can't just copy data because cloning states is illegal in the quantum constitution. So engineers looked at xenodynamics instead. Watch carefully enough, and the system stalls before errors spread. It's like freezing a bad haircut before the barber can finish botching the style. The observation doesn't fix the mess, but it prevents further disaster long enough to intervene. Meanwhile, optical technologies join the party. Photons are slippery. They refuse to sit still for anyone. But laboratories discovered that by continuously probing their paths and interferometers, they could control interference patterns. Imagine a cat that always bolts across the kitchen unless you glance at it, in which case it tiptoes along the wall. Observation reshaped the very choreography of light, turning randomness into something closer to obedience. That obedience, of course, could be sold as a feature for precision sensors. Not to be outdone, nuclear physicists asked if observation could regulate radioactive decay. If measurements could nudge nuclei into faster breakdowns, maybe waste disposal could be accelerated. Why wait centuries for isotopes to calm down when you could rush them with well-timed scrutiny? Picture a radioactive barrel in storage, and every so often scientists shine metaphorical flashlights at it to make it decay faster, like clapping at a reluctant performer until they finally exit the stage. The environmental agencies haven't signed off, but the thought alone shows how quickly a paradox can morph into an industry pitch. On the flip side, slowing processes is just as tempting. Imagine extending the lifetime of quantum states used in communication channels. Quantum networks promise unbreakable encryption by sending entangled particles across vast distances. The problem? Entanglement usually unravels faster than a cheap sweater. With the Zeno effect, though, you can stretch the coherence window. By watching entangled particles at precisely chosen intervals, you keep them from collapsing too soon. It's the technological equivalent of holding a relationship together by checking each partner's texts every 5 seconds. Obsessive? Yes. Effective? Also yes. Of course, implementing this isn't trivial. You don't just set a stopwatch and squint at atoms until they comply. You need ultra-fast lasers, superconducting detectors, vibration isolation that borders on ridiculous, and graduate students willing to babysit equipment like anxious parents on their toddler's first day at daycare. Every experiment becomes a war against noise. A stray phone vibration, a wandering speck of dust, or a janitor's sneeze could ruin weeks of data. Yet even with all those hazards, the results remain consistent. Timed observation reshapes quantum behavior. Economics inevitably got involved. If Zeno control could extend qubit lifetimes, speed up decay, or freeze delicate states, then industries smelled patents. Corporations began investing in measurement-driven stabilization schemes, essentially trying to monetize attention. Observation became intellectual property, a product in itself. The irony is staggering. For millennia, humans thought watching was passive. Now companies draft legal documents claiming exclusive rights to look at atoms in this particular way. Imagine trademarking the act of staring. Welcome to capitalism's strangest chapter. Even the military peeked in. If you can control decay rates or energy releases by adjusting observation timing, you might influence weapon designs. Faster radioactive decay could mean more compact devices. Longer coherence could mean more secure communication. The Zeno effect went from philosophical nuisance to geopolitical bargaining chip in a disturbingly short time. Nothing motivates funding like the promise of outstaring your enemies. And yet, the deeper these technologies burrowed into practical systems, the more fragile they became. The closer you push toward exploiting Zeno timing, the more sensitive your instruments must be. It's like trying to win a race where the track gets narrower every lap. Engineers dream of reliable Zeno-based devices, but reality insists on tripping them with thermal noise, stray fields, and the sheer indifference of probability. Every attempt to commercialize the phenomenon turns into a reminder that nature doesn't like being bullied for profit. Still, progress marches on. From frozen qubits to coerced photons, the effect has crept into the toolkit of applied physics. Not because it's easy, but because it offers control that no classical knob can match. Measurement becomes a dial. Turn it fast and you stall, turn it slow and you accelerate. For the first time, staring isn't just rude, it's programmable. And the most unsettling part? If technology can sculpt reality through observation schedules, then human tools aren't just recording the universe, they're dictating its tempo. Which raises the darker question. What happens when observation leaves the lab and collides with the chaos of everyday existence? Outside of laboratories, the Zeno trick doesn't stay politely in the background. It stalks everyday reality, smirking while you pretend the world follows neat classical rules. Because once you realize timing and observation can sculpt outcomes, it's hard not to see fingerprints everywhere. Start with traffic lights. Every driver knows that staring at the red lamp feels like it makes it last longer. You swear the universe is mocking you personally, and physics nods politely, saying, "Yes, actually, your attention can delay events, just not at the scale of your commute." What feels like cosmic cruelty is just your brain echoing a quantum truth. Watch too closely and change stalls. It's the Zeno effect pretending to be rush hour psychology. Then there's gambling. Casinos thrive on observation bias. Players hover over roulette wheels or slot machines, convinced their gaze has influence. Ironically, quantum mechanics agrees. In microscopic worlds, observation really does alter odds. Unfortunately, slot machines aren't superpositions. They're engineered scams with LED lights. Still, the delusion is rooted in physics behaving like a prankster. When you do measure the tiny stuff, you shift reality's course. Even your phone suffers from this dynamic. Loading bars appear frozen when you stare at them, only to sprint forward once you look away. It's not mystical. It's interface design exploiting your impatience. But the eerie resemblance to Zeno-like freezing makes you wonder if software engineers secretly studied quantum mechanics or just enjoyed torturing users. Either way, watching stalls the bar, turning you into the unpaid lab rat of modern design. Psychology keeps piling on evidence that observation alters behavior. People act differently under cameras, bosses, or even the suggestion of being watched. Crime drops when fake CCTV signs are posted. Employees work harder when supervisors hover, and cheating dips when exam halls have mirrors. Humans collapse into obedient states like particles collapsing under detectors. The difference is that atoms don't sigh when you stop watching, while workers do. Surveillance culture thrives on this principle. Entire cities now operate as quantum systems with too many eyes. The more cameras, the more frozen behaviors. Jaywalkers hesitate, shoplifters reconsider, and crowds shuffle with awkward caution. It's the Zeno effect scaled up to social engineering. The act of monitoring stops natural evolution, not of particles, but of people. You don't need equations to see it. Just watch a public square bristling with CCTV and count the stalled movements. And it doesn't stop at behavior. Attention rewires economics too. Stock markets are infested with traders monitoring every millisecond. Algorithms buy and sell so rapidly that the market itself becomes a jittery quantum system. Constant surveillance stalls some opportunities, while poorly timed trades accelerate collapses. Finance, in other words, has become a giant Zeno laboratory where fortunes freeze or decay depending on observation schedules. Your retirement fund is basically qubits in a suit. The entertainment industry weaponizes the same trick. Reality TV contestants behave stiffly under relentless cameras, freezing into caricatures. Performers collapse into exaggerated versions of themselves, not because they're fake, but because constant observation forbids natural progression. Every confession booth moment is a superposition collapsing into melodrama. What's billed as authentic is actually physics meddling through surveillance. The producers just happen to monetize it. Even relationships echo this dance. Overanalyze your partner's every text, and you paralyze the natural flow. Ignore them completely, and events accelerate into disaster. The survival of romance depends on spacing your measurements carefully. Too frequent, and you stall affection into awkwardness. Too infrequent, and the system decays faster than uranium in a particle accelerator. Dating is, apparently, a Zeno experiment nobody consented to. And the creepier angle? Technology is amplifying this to absurd levels. Smart devices watch everything, heartbeats, sleep patterns, GPS locations. Each new data point is another measurement. The more sensors track your body, the more they risk influencing it. Wearables can nudge people into healthier routines, but they also turn life into a monitored treadmill where spontaneity suffocates. Observation doesn't just record behavior. It freezes it into loops of optimization. Your fitness watch is basically a Zeno machine disguised as a lifestyle coach. What's unnerving is how seamlessly this quantum principle scales up from electrons to societies. Atoms stall under observation, people freeze under scrutiny, and systems buckle when watched too closely. The through line is unmistakable. Monitoring changes outcomes. The universe didn't design itself for passive voyeurs. Watching is meddling, whether in a chamber filled with atoms or a city filled with cameras. Yet the unsettling part isn't what's already happening. It's what might happen when observation is no longer human. As AI surveillance grows, machines will measure us constantly, with intervals shorter than any human could manage. If timing is everything, then automated observation could rewrite the tempo of social existence in ways no law or ethicist can anticipate. It's quantum meddling scaled into a political problem, where the cadence of life depends not on natural rhythms, but on how often machines decide to check in. And if that principle holds, the line between physical reality and lived experience blurs into something grotesque. A world where every glance, every sensor ping, every recorded interval isn't just collecting data. It's steering existence down paths we don't yet recognize. Physicists love to pretend they're dispassionate, rational monks of truth. But throw the Zeno effect into the room, and suddenly the lab coats turn into gladiators. Because when observation dictates the tempo of events, the question becomes, who gets to decide what counts as observation? And that's where the real brawls begin. One camp insists only conscious observers matter. According to this view, reality waits politely until a human brain checks in before collapsing into a definite state. Sounds flattering, like the universe is your personal butler, pausing until you're ready. The problem is that this theory makes physics sound like a cosmic improv show. Nothing happens until an audience claps. It's comforting for philosophers, but a nightmare for anyone trying to build reliable technology. The rival camp throws humans out of the equation entirely. Detectors, sensors, even random molecules can measure by interacting with systems. Observation doesn't require eyeballs or awareness, just entanglement. This version is brutally democratic. Anything that interacts counts as a witness. Drop a photon into a detector, and boom. Collapse happens whether or not a grad student is there to clap politely. Reality doesn't need you, it just needs gossip between particles. The fight isn't just academic. If only consciousness collapses states, then human perception shapes the timeline of reality. If any interaction counts, then humans are irrelevant, drowned out by the deafening chatter of the cosmos. Pick one, and you get a universe that revolves around awareness. Pick the other, and you're just another noisy molecule in the crowd. Neither option leaves much room for comfort. Naturally, experiments tried to weigh in. The delayed choice experiment mocked both camps at once. Shoot a particle toward an interferometer, decide at the last second whether to measure its path, and the particle obliges, retroactively. It behaves as though it knew your decision all along. Cause and effect stumble over each other, leaving scientists with the creeping suspicion that the timeline itself isn't as straightforward as calendars suggest. The philosophical consequences hit like a slap. If observation can rewrite whether an event already happened, then past and future aren't politely separated. Measurement digs its claws into time, leaving physics with the awkward duty of explaining how tomorrow's choice influences yesterday's history. Not exactly the clean, deterministic march Newton promised. Interpretations multiply like weeds. The Copenhagen loyalists say collapse is real, measurements dictate outcomes, and everyone should stop asking embarrassing questions. Many worlds enthusiasts argue there's no collapse at all, just endless branching timelines where every possibility plays out, leaving you stranded in whichever branch matched your observation. Objective collapse theorists suggest reality has its own timer, collapsing states whether or not anyone watches, like a cosmic smoke alarm. Each camp publishes papers, waves equations like sabers, and quietly hopes the other groups run out of grant money. And amid the fighting, the Zeno Effect smirks. Because no matter the interpretation, the fact remains. Fiddling with measurement timing warps outcomes. Whether it's humans, machines, or reality itself doing the measuring, the tempo shifts. That brute fact laughs in the face of tidy philosophical camps. You can argue about what really collapses all you want. The stopwatch doesn't care. What unsettles the most is how this undermines causality itself. Science usually relies on neat chains. A causes B, which triggers C. But if watching can alter the rate of change, or even reach backward into events that should be finished, the chain snaps into loops. Suddenly, the act of looking isn't the caboose of reality. It's the switch operator, rerouting the train in real time. Cause and effect trade places, leaving humans clinging to explanations that sound more like excuses than laws. This makes physics look suspiciously like psychology. Just as people behave differently when they know they're being watched, particles act differently when measured. Surveillance alters outcomes at both scales, blurring the supposed gap between human society and atomic behavior. Reality itself seems allergic to being passively recorded. The moment you try, you've already rewritten the script. And that script keeps getting stranger. If observation tinkers with the timeline, then free will is on the chopping block. Do your choices determine outcomes? Or do outcomes determine your choices once you peak? Every measurement looks like a negotiation with the universe, where neither side admits who started the conversation. The arrow of time begins to wobble, and physics, the discipline that once promised absolute clarity, starts to sound like it's trapped in a Kafka novel. Meanwhile, technology marches ahead anyway. Quantum computers hum, qubits stall or accelerate, particles collapse into obedient states, and the debates rage on in journals that nobody outside academia reads. But beneath the experiments and devices, the haunting implication lingers. If observation decides what is real, then reality isn't a solid backdrop. It's a performance, rewritten every time someone takes attendance. And the curtain hasn't dropped yet, because the question no one can silence keeps humming under the noise. If reality waits for observation, then what, or who, has been watching all along?